Hello, everyone. My name is David Lara. I am a fellow student in this CIS 231 class for assembly language. Today, I'm going to be going over my lab number 7 prompt and response. Before I get into that, let me just go ahead and show you guys the PDF. I mean, we should all be familiar with it. So this is a floating point unit lab. So it's meant to deepen the student's understanding of performing MASM operation using the floating point unit. This assignment will help you work effectively with floating points in MASM. Um, and basically the prompt is prompt the user for coefficients a, b, and c of a polynomial in the form of ax squared plus bx plus c equal to 0. Calculate and display the real roots of the polynomial using the quadratic formula. If any root is imaginary, display an appropriate message. If we have one real root, repeated root, specify an appropriate message with the root value 1. Otherwise, write that we have two distinct roots and list them. Paste your code in a screenshot of the output in a Word document and so forth. So basically what we're being asked of is to utilize the floating point unit in our code, basically adding that into all our knowledge on what we've learned so far. In kind of a way that it was easier for me to understand is this MASM program that I wrote uses the quadratic formula to solve the equations in this form. Let me see. Let me load it up. So it's on this side. All right. So right here, we're in my Visual Studios. This program was written using only the Irvine 32 library functions, just because primarily in this class is what we're going to be utilizing. It takes inputs from the user and calculates real roots using floating point operations learned from the textbook. So a lot of this stuff, I was unfortunate to miss 2 weeks worth of class. So I learned from the book. I did my best to read it, understand it, and then whatever gaps of knowledge that I didn't have gaps of knowledge that I had when it came to working on this assignment, I utilized, YouTube as a main source of, troubleshooting. I ran into a lot of the issues when trying to implement the logic behind the operations and order of operations and so forth. So, most of this, if not all of it, was self-taught from the book, copy pasted from the actual Irvine website as well. Um, so as we start into part one, we're going to start with my data section up here. So I'm kind of just calling it part one just because as I explain everything. So in our data section here, I'm defining all the messages and variables. So these are the prompt messages and error messages shown to the user. Prompt A, B, prompt A, prompt B, prompt C. All of them are string bytes indicated by the comma and 0 at the end to know that the string is ending. They're going to ask the user for the coefficients of the equation. So each of them will ask for a value for A, a value for B, and a value for C. Each careful not to be 0. I know that wasn't asked in the lab, but it helped me kind of understand it a little better when I handled all these calculations by hand, just to kind of test that the logic was, foolproof. Once we get down here to the output messages, this is what is outputted to the user after every calculation is done within the code. So we have the message imaginary, message 1 root, message 2 roots, root label 1, and root label 2. So these are the outputs when necessary. So if we have if we have a solution that is an imaginary root, then this is the only message the user will get. They will not get any of these. And we're using the jump instruction to kind of jump between each prompt so that, we're handling the calculations within the lines of code, but everything outputted to the user is just appropriate to what fits the solution best. So we're not going to see multiple of these. We're only going to see one of each, two of each, so forth, just whatever's appropriate. And that jump instruction really comes in handy once we get to that point. But this is basically used to label the type of solution and the components within the solution. I also created variables for the computations that are going to happen within the code. So we have A as a double word. We have B as a double word. There's an error that I kept running into when it came to C. So I guess C is such an ambiguous title slash category slash label. the code will not accept it as a variable name. So I figured this out on YouTube, but basically my fix for it was to add value to the end of it. So it's still C, but we're just adding that little tagline to the end of it just so that the code can accept it and the code can utilize it. Once we get down here, disk is short for discriminant, so this is what's going to be happening within the square root. And that's basically b. Well, it's actually going to be b squared minus 4ac. That's what we're categorizing as the discriminant here. And all of this kind of evens out nicely, and I'll kind of explain it right now. So num1 will be a Q word because we do not know what it is. So it's used to temporarily store the numerator for root 1 during floating point calculations. So this is not really a known until the calculations begin to occur. So that is why it's Q word. Um, I think we were given a solution in class when the professor was writing everything on the board that said to just put equals question mark. When I was searching for that specific instruction to see how I could utilize it, I got confused. So this response came from the textbook. So we're going to go down to the code now, but that's basically the data. So in the code section, the program starts with our main proc, nothing new. We first ask the user to enter the values for A, B, and C. So the way that it's done is everything will be prompted consecutively. So insert A, insert B, insert C. Then the calculations will occur. So I didn't really want to pause in between or do anything that required step by step during those instructions. I wanted everything to be asked for at once. That way the user can just input whatever they needed to, and then the code can handle the rest. So for A, we include a check to make sure it's not 0. So we want to compare EAX to where the value is stored to 0 to make sure that it's not 0. Because if A equals 0, then it's not a quadratic formula. So once we get valid inputs, we store them in the appropriate variables. So you'll see a lot down here. Obviously, once we get to the C and the B, I'm not comparing for 0 because only A cannot equal 0. So I'm not sure if I mentioned that earlier. Okay, yeah, I did. Okay, so that's what I included to the user. Okay, so moving on. So we're gonna jump to read A. See, we're using the jump instruction a lot. So we'll move down, and this is where we start to compute. So this is after collecting the input that we gathered and was necessary for the user, then we're going to go ahead and calculate the discriminant using b squared minus 4ac. So this tells us whether we have two distinct real roots, one repeated root, or imaginary roots. So as you can see here, we're moving the value of b into EAX. We're going to multiply b by what's in EAX. We're going to move EAX into EBX. So this is basically EBX is equal to b squared. We're going to move the value of a into EAX. And then we're going to multiply EAX by C value. We're gonna multiply 4 by the value of EAX, so that's gonna be equivalent to EAX equals 4AC. And this is where the subtraction comes in. So subtraction is EAX from EBX. And then we're gonna move EBX into discriminant. And this should give us EBX is equal to b squared minus 4AC. We're going to compare that value to 0, and depending on what it looks like, that's when we'll jump to the necessary functions down here. So if it's a discriminant, it'll be less than 0 for here for the imaginary, and that's when we'll output. If it's only one root, then discriminant is equal to 0. If it's two roots, then the discriminant is greater than 0. So this case for imaginary roots, if the discriminant is less than 0, we print a message saying the roots are imaginary. Okay. So this is part of the floating point root calculations now as we break it down. So first, we're going to load negative b into the floating point. This is where our floating point calculations begin, here in the root 1 column. So we're basically going to load negative b into the floating point stack. So down here, we'll go ahead and calculate negative b, load it in, and then we're going to utilize the functions given to us in the floating point to be able to do the calculation for the square root. So we're taking the square root of the discriminant, and then we're going to add that to negative b. So I broke it up step by step here. In the beginning stack, we have negative b stored already. So that's what we're calling down here. Then the stack becomes what we're adding to it. So stack one is still negative b, but since we added the square root of the discriminant into stack, this one takes priority. So it's actually last in, last out. Okay. Then we're going to store that numerator temporarily into the num1 that we designated that was unknown prior in the beginning. Then we're going to load 2a into the floating point unit and divide the numerator by the denominator. So in our stack, we have 2a, and this is where the division occurs with the floating point. So we're calling the stack, and we're dividing the stack by each other. So the numerator is divided by 2a. Notice how they're all stored in the float with the floating point instructions. Okay. So the result is printed as floating point number using right float. So that's where we are right here. Using right float. And we're going to offset the root label 1 just to tie it so that we know that that's the solution here. And then this down here will clear the FPU. So this will enable the stack to start again to resume. So root 2 is similar. We do the steps, but subtract instead of add. So instead of having the addition, we're having the subtraction down here to be able to better utilize the appropriate calculations and keep the logic. Since one value would be positive and another value would be negative when we're using the plus minus in the quadratic formula. So using the FPU stack carefully, we're avoiding errors, especially by storing intermediate results and avoiding the FD-IVR problem. So using the floating point unit stack carefully, we're avoiding errors, especially by storing intermediate results. And this is where we get to the final problem. We jump when we're done, and done is to exit the problem. So all of these calculations are occurring based off of a need basis. So that is why the two real distinct roots occurs last, because that'll determine once the calculations begin to occur, then we can determine whether it's imaginary, whether it's not, based on the initial comparison in the beginning. So all that really matters at this moment is the discriminant. Once the discriminant gives us a value that we know will be logically appropriate, then we know what step needs to be taken. And the program does a good job of keeping that concise and keeping that clear. It can solve any quadratic equation and handles all three of these root cases very easily, very fast. So it was a great way to showcase everything learned in that chapter, in chapter 12 of the material. And before I go, I do want to kind of output some samples. So just to kind of show that the code is running, let me build the solution. Okay, build complete, 0 errors. All right, so we'll go ahead and debug now. And then we'll go ahead and test for imaginary first. So I did this by hand just to make sure that it was correct. But for coefficient A, we're going to input 2. For coefficient B, we'll input 2. And coefficient C, we'll input 2. This should give us imaginary roots. When you handle the calculation in hand, similar response, similar output. So let me go ahead and test again. And this time I'll showcase what happens when you put 0. Okay, so it's going to prompt the user that the coefficient cannot be 0, and it's going to ask again. So this was something that took a while to figure out as well, just because I wanted to not stop the user from inputting ABC after the incorrect input. So now if we continue and we give them the correct input, 1, then we can move on, no problem. So we'll go ahead and do 1, 2, 1, and that should give us only one real root, which is -1, and that is correct, by the way. So we'll go ahead and exit that. Next, we'll do 2 roots. So let's do 2 roots. So 2 roots here would be a 2, -4, and -6. This should give us root 1 is equal to 3, root 2 is equal to -1, which is also correct. So there's some logic problems that I had in here when determining whether this was running or not. And for the majority of it, the floating point instructions were very clear in the book, very clear on the website for Irvine. It just comes down to logic problems that I couldn't really get around, couldn't really explain. So, for example, one specific issue I found was when calculating my first sample, which was going to be A is 1, B is -3, and C is 2. So I handled all these calculations by hand prior just to make sure the code was correct. But when I ran this, my root 1 should be 2, and my root 2 should be 1. But look at what happens when I output. So we're given 5 for root 1 and 1 for root 2. So nowhere in the code can I find an error that dictated that it was a logic problem with the code and like, I was doing something wrong. Um, this was my root 2 example. This is my first example too. And when I couldn't get this one to work, I calculated another example and that example worked just fine. So I think it boils down to there's a minimal gray area for errors. There's room for error in here. Um, it's left to be seen whether this is something that I can fix just because I was like super deep into it. I did my best to kind of research it and um I I left no page unturned. I went through every avenue of support I could think of. Um but when it boils down to it, that's the only logic problem I was coming across. Well, thank you for watching. I hope that this is very helpful and I appreciate your time and have a great rest of your day.